We talked about the definite integrals and other relations between the definite integrals and the net area, and also the total area between the curve and the x-axis and the line passing through the point x is equal to a and the point x is equal to b, or the y-axis and point x is equal to b. Today I want us to actually talk about what I call the fundamental theorem of calculus. So let me write this, the fundamental of the fundamental theorem of calculus. So what it says this: suppose the function f is continuous. You have a continuous function f. So you have a continuous function f on the interval. So this function f is continuous on the interval ab, right? So there are two conditions here. There are two implications. If g of x is equal to the definite integral from a to x of f of t dt, then if I take the derivative of this function with respect to x, then our g prime of x is going to be, I take this x here. Take note that the only thing that is here is x. So this x here is the one that we just plugged into this function. So we end up having f of x. So whatever the function that I have, I just take this x here and then plug it inside to get that. That is what is basically happening there. The second condition here is saying this thing: if I have the definite integral from a to b of f of x dx, it says that the definite integral is just gonna be the capital letter f of b minus f of a, right? Where f is any antiderivative. It's any antiderivative of f. That is, if let's say you are taking f prime of x, you're supposed to end up getting f of x. This one we have been doing it every now and then, and we knew it as the evaluation theorem, or we used this to find the net area under the curve. Also, it is actually the definite integral, so we are familiar with number 2. The only issue we have is number 1. In other words, we need examples that are concerning number 1. Again, what is important here is that here we are only having an x, and then you can just take this x and plug it inside to get the derivative of this function here, so that you end up, you can see there is a t, you just take this x and plug it inside, and then you get f of x, and then you will get the derivative. Let's look at the examples. What are the examples saying here? So you have examples. So we have our examples. So number 1, what is number 1 saying? Use this question is saying use part 1. Let me just say use the fundamental theorem of calculus, to find the derivative of each of the following functions. So you wanted to find the derivative of each of the following functions. A is given as you have your g of x, and g of x is the same as you have 1, you have x, and you have 1 over, you have t cube, you have t cube plus a 1, and then you have a dt, and then you have a b. B is saying you have g of x, and g of x is a definite integral from 3 up to x of the function e raised to t squared minus a t, and then you have a dt there. And then you have c. C is saying you have g of x, and g of x is actually the definite integral from 3 up to the function x squared, and then minus x, and then you have e raised to t, and then you have dt, and then you also have your d. Your d is you have your g of x. Your g of x is the integral from 3 up to 2x, and then you have e raised to t squared, and then minus a t, and then you have a dt. And then number two, I want you to find the function. So I want you to find the function f and a number a such that 6 plus the integral from a up to x of f of t divided by t squared, and then dt is equal to 2 times square root x for all x greater than a 0. So we are having these questions here. So I want us to answer each of these questions. We want to find the derivative of this function, the derivative of that function, the derivative of that function, the derivative of that function, and also find this value a here and find this function here. How do we do that? So these are not so hard at all. Let me write the solutions. Right. Let's start with number a. Right, we are having our g of x, and our g of x is actually the definite integral from 1 up to x, and you have 1, and then you have t cube, and then you have a plus 1, and then you have a dt. So we're having that. Now we are looking for dx of g of x, right? Because we are looking for that, we have to take the derivative on both sides. Of course, we have 1 raised to x, and then have 1, and then you have t cube, and then you have plus 1, and then you have a dt. And the next thing, of course, this one is just gonna be our g prime of x, fine. But the derivative of this, we said that if you are having a function of this type, g of x is equal to, you have a function like this and you have x there, all you need to do, replace this t by that x, and that is actually going to be your derivative. So that's what we are going to do here. So the derivative of this, where there is a t, I'm just going to plug in an x there. So we'll end up having 1 divided by x cubed plus a 1. That is actually the solution to our problem, which is as easy as that. Let's look at number b. What is number b? Number B, we had our g of x, and our g of x was from 3 up to x, and we had e raised to t squared minus a t dt. So we are looking for the derivative, which is d dx of g of x. Why am I having an x here? It's because we have an x there. So the derivative needs to be d dx. And then I have to take it on both sides. And then, of course, we will have from 3 up to x e raised to t squared minus t dt. What is important here, I want you to realize we have an x there as an upper limit of integration. So this side we're still gonna have g prime of x equal to, and because we are having a nice x sitting there, the fundamental theorem of calculus is saying take this x as it is, replace the t, that is actually going to be your derivative. So we'll end up having e raised to x squared minus x. That is actually going to be our derivative for this function using the fundamental theorem of calculus, because the fundamental theorem of calculus is saying that if you're having that, replace that, and then you will get that. That's simple as that. Let's look at the let's go to number C. What is number C saying? Number C is saying we have g of x, and g of x is moving from 3 up to x squared minus x of e of t dt. So what we wanted to end up doing here is very simple. I wanted to have d dx on both sides of g of x. Like I said, this x is that x there, and then because I'm taking this, I have to take it on the right to d dx of the integral from 3 up to x squared minus x of e of t dt. So that is actually what we are getting to here. One thing for sure, on the left hand side, I'm going to end up having g prime of x. On the right hand side, I am still going to have d dx, and then inside here I am going to have a 3, and then I'm going to have an x squared minus x, and then I have an e, and then I have a t, and then I have a dt. Now, of course, I have to close this side. What is the fundamental theorem saying? The fundamental theorem is actually saying that whenever you have an x here sitting alone, all you need to do when you want to find the derivative, take that x and plug it in there. So if this x is alone, that's when you plug it inside here. But if it is a function, then we need to change it so that the upper limit is just a variable sitting alone. We don't want to find a function. So how do we end up doing that? So if you look into this part here, I want you to realize that we have x squared minus x, and instead of having just x, we are having x squared minus x. So we need to change this part here so that we end up having a one variable that is sitting there, so that we can just take that variable and then plug it in the value of t, and then that is going to be easy for us. So because we're not having an x alone here, we need to change that. So what we do, we just say let u equal to that thing that is sitting in the value of x, because we want to have an x there. And then we say let u equal to x squared minus x. Then if I have a u there, you can see that if I take du with respect to x, what am I going to get? The derivative of this is going to be 2x minus a 1, because the derivative of this part is going to be 2x, the derivative of that is going to be a 1. And then why am I doing that? Because if I'm going to replace that, I also need to replace this x here, this dx. So let's solve for dx. This simply means that our du must be equal to 2x minus 1 times dx, because there's a 1 there I cross multiplied. And then from there, solving for this one, I have to divide on both sides. So I'll have du divided by 2x minus 1 is equal to a dx. So going back to this thing that is there, we can actually see that now our g prime of x is simply going to be d. Instead of this dx here, I'm going to plug in that. Remember that I have a big division sign there. I will have a du divided by 2x minus a 1. And then, of course, inside here, I will end up having 3. Here, I will have a u now nicely. I have e raised to t, and then I have a dt. Can you see how easy this thing is? And then when you focus on this, you will find out that I can change this division to multiplication. So if I'm changing this to multiplication, this becomes a numerator and this becomes a denominator. And then we end up having 2x minus 1 times du of this nice thing here, which is going to be 3. And then I have a u, and then I have an e t dt. And if you look into this one here, you will find out that what we actually end up having, you have a 2x minus a 1 nicely sitting there. And then when it comes to this, you use the fundamental theorem of calculus, which say take this variable, as long as you have du and you have a u there, take this variable and just plug it there. So we'll end up having e in the value of t. I'm going to plug in a u, and of course this is going to be 2x minus 1 e. What was our u? You go back. Our u was actually x squared minus x. So you will end up having an x squared minus x. So that is actually the solution to number C. What is important here, other people, what they usually do, they just take this and plug it in the value of t and get the derivative and then multiply by the derivative of that. That is actually correct. Others, they do it this way. I prefer to use it this way because it becomes straightforward and is also kind of linked to the substitution rule. That's why I follow this. I know that others don't approve this because of that D, but I like it because it actually makes it easy for a student to understand the substitution rule, especially if they have done the fundamental theorem of calculus. So that is what is important for me and also for the student, of course. So that's what we do. Let's go and do number D. What is number D saying? Number D, we are having our g of x, and our g of x is the definite integral that is moving from 3 up to 2x of e raised to t squared minus a t, and then you have a dt. Of course, we want to find the derivative. Take d dx on both sides because this is x. If this was t, we're going to take d dt on both sides. And then, of course, here you will end up having g of x. This must be equal to, and then you have a 3. No. You have to take the derivative on both sides. So I have to take d dx on both sides. And then you have a 3. And then you have a 2x there. And then you have an e. And then you have t squared minus a t, and then you have a dt. And then when it comes to this one, we have g prime of x, and then you come to this. When you look into this side, the issue we have, we don't have x sitting alone there. So if we had this and we have that, because we want to measure this one and that one, we have dx and we want to have x there. So what is sitting in the value of x there, we let it to be equal to u. So what we end up getting here, we just say let u to be equal to 2x. so that when I'm taking du dx, the derivative of this u with respect to x is going to be just a 2, and when I'm cross multiplying, I will end up getting du equal to 2 times dx, or simply put, you have du divided by 2 is equal to dx. And then we come here and solve this equation. Then this one, this is just going to be g prime of x. And then when it comes to this side, I'm going to have a d. In the denominator, I will end up having a du over 2. And then, of course, I still have these brackets here from 3 up to. Now, instead of having 2x, I know that 2x is just a u. So I'm going to place a u there. And then the next thing inside here, I still have an e raised to t squared minus a t. And then I also have dt here. I have to close. That is what is important. Of course, the next thing is just simplification. Like I said, this is g prime of x. And then this one, I change division to multiplication. So this one here will still have a d. And then if I do multiplication here, let's say I have this d, I will end up having this is a division, so I'll end up multiplying. The denominator becomes a numerator, and the numerator becomes a denominator. So we're having something of this sort. That is why I say that we have a 2 times du. And then, of course, inside here I have the s here, and then I have a u, and then I have e, and then I have a t squared minus t, and then I have a dt. And then if you look into this, I have du, I have a u. Now they are meshing these two, so I end up having a 2. And then looking into this and that, because this is just a u, this is du, I can take this and replace the value of t there. So I will end up having e raised to u squared minus u as the derivative, or simply put, you have a 2e. What was u is going to be 2x squared minus 2x, which is just the same as 2e raised to 4x squared minus 2x. That is actually the final answer to our problem. So that is one of the final answers that we can get. Again, when you are having, just a quick summary here, when you are having something that is straightforward as this, just take this x and replace the t. That is going to be your derivative. The same thing here, if you are having an x sitting there, take this, replace these t's. That is going to be your derivative. But if you are having this thing here, you let it to be your u, and then you start replacing it by u, and then you start replacing this by du times something, or du divided by something. That is what we're trying to do here. And then once you actually set your u, find the derivative of u with respect to x, and it's going to be that, and then you cross multiply and solve for this dx. Once you get it, you replace the dx, you replace the u, and then after that you move up until you are there. And once you have a du and you only have a u there, that's when you can just take this, replace this t, a u, like I did there, and then I still have that as it is. And then next I replace this u by the original function. That's simple as that. The same thing we did it here. Let's go to number 2. Let's go to number 2. What is number 2 saying? Number 2 is saying this nice thing here. 2 is saying find the function. Find the function f and a number a such that if I take 6 and I add the definite integral from a up to x of f of t divided by t squared dt, I'm always going to get 2 times x for all x greater than 0. So this whole thing is always going to be equal to that. Now I want us to find, the question is saying, we want us to find f of x. What is going to be our f of x and what is the value of this a there? This is not hard, because once you are having a function here and you have this and you have an integral somewhere there, all you need to do, and also this one, we can use the fundamental theorem of calculus. So the first thing that we need to do here, let's take the first derivative here. This is the solution. Okay, let me explain here, because it seems automatic when we are doing a fundamental theorem of calculus. Just know that, okay, we take derivatives, we do that. We wanted to solve for f of t, but then now the problem we have the integral. So if we are having an integral, we want to remove an integral, because an integral is actually finding the antiderivative. So to remove the integral, we need to take the derivative throughout, so that this is actually gone and we can start solving for f of t. I hope you can see what I'm trying to say here, that whenever you have that and you want to remove it, you have to take the derivative throughout so that it is gone. So that is the first step to actually solving for this. So let's take the first derivative with respect to what? Because this side we are having an x, so we'll take it with respect to x. Because here also we are having something that is matching that, we're going to take this throughout with respect to x. And then of course we take the derivative of 6 plus the integral from a to x of f of t divided by a t squared, and then dt. And then of course, because we do not have this, we have to take it on the right hand side also. So you have 2 times the square root of x. And of course, what is the derivative of 6? That's a 0. So you have a 0 plus the derivative with respect to x of, I have the integral from a up to x of f of t divided by a t squared, and then I have a dt there. And then this side I have a 2. No, this is not a plus. I have to say equal to. I have a 2 times dx of the square root of x. Of course, the square root of x is the same as just x raised to 1 over a2. The next thing here is we use the fundamental theorem of calculus, because I have a dx and I have an x there. So take this x and replace the t. That's what the fundamental theorem of calculus is saying. The derivative of this is we are going to end up having f of, in the value of t, I'm going to plug in x because x is isolated. So I'll have an x there divided by x squared. That is going to be this derivative when we're using the fundamental theorem of calculus. And then we'll have a 2 times the derivative of this is going to be bring the exponent down, keep the x, and then subtract a 1 there. That's how simple this is. So we have f of x divided by x squared is equal to this, and that will cancel out, and then this will cancel out, and now we'll be left with x raised to minus 1 over 2. And then of course the next thing is to cross multiply. So I cross multiply, so I end up having f of x is equal to x squared times x raised to minus 1 over 2, which is simply x raised to 2 minus 1 over 2. Let me write this nicely. So I have a 2 minus 1 over 2, right? So I'm having my f of x equal to, I have x, 2 is the same as 4 over 2, right? Minus 1 over 2, or simply put, we are having x, and then in the exponent the common denominator is 2. 4 minus 1 is a 3. So I can say that our f of x is going to be the x raised to 3 over a 2 using the fundamental theorem of calculus. But if you look here, this question is saying find f and a number a. How do we find the number a? I mean, we already have this function here. Then we can take the definite integral, solve, and then see if we can get a. Okay. Since 6 plus the integral from a to x of f of t divided by t squared dt is equal to 2 times root of x, then 6 plus the integral from a to x f of t is saying plug in t in the value of x, so we'll end up having t raised to 3 over 2 all over t squared times dt must be equal to 2 square root x. And then once you work this thing out, you'll find out that you're having x plus, and then this one here, let's first actually simplify here. So we'll end up having t raised to 3 over 2 minus a 2, because when dividing powers of the same base, you subtract exponents. This was a power 2, so we subtract it. And you know that 2 is the same as 4 over 2, and then you have a dt, which is the same as 2 square root x. And then you still have a 6 plus, and then you still have this definite integral 0 to x. And then when it comes to this, you are just having a t. 3 minus 4, that's minus 1 over a 2, because 2 is a common denominator. And then you have a dt equal to 2 square root x. And if you look carefully on this, you can still have your 6 plus, and then this part here is going to be very nice. The particular antiderivative of this is going to be t. You have a minus 1 over 2. You need to add a 1 and then divide this by the new exponent plus 1. And then of course we want to evaluate this when x is equal to a and when x is equal to, not x, because the variable is t, when t is equal to a and when t is equal to x, and this whole thing is equal to 2 root x. The next thing is simply we'll end up having 6 plus and then here what are we going to get? I want you to realize one that is the same as 2 over 2. This 2 over 2 is coming from that, and then 1 is the same as 2 over 2, 2 over 2, and of course 2 over 2, this is a common denominator, and 2 minus 1, I know that is just a 1, so we'll end up having a t here raised to 1 over 2 divided by 1 over 2 evaluated when t is equal to a and when t is equal to x, and then this is equal to 2 root x. The next thing that we want to do here is 6 plus, and then you try and look for this. You know that we have t raised to 1 over 2. We change the division to multiplication. When we are changing it, the numerator becomes the denominator and the denominator become the numerator. And of course we want to evaluate this when t is equal to a and when t is equal to x. We know it is equal to square root x. And then the next thing that I want you to realize is that we have a 6 plus this one here, we know that's going to be 2 times t raised to 1 over 2, and then evaluated when t is equal to a and when t is equal to x, and we know that this is the same as square root of x. And t raised to 1 over 2 is the same as the square root of t. That is what is important here. And then we have a 6 plus, and then you can take this x and plug it in, so you will end up having a 2 root x minus 2 root a. That is what is important here, because now we are plugging in, we are actually going and evaluating at these points. You know that this is coming from the fact that the definite integral from a to b of f of x dx is equal to f of b minus f of a. So this part here belongs to that part, and then of course we're plugging it to get that, and then plug this, you get that. This minus here is the minus that we have there. I hope you can see what we are actually doing here, and then you end up having 2 root x. So you have 6 plus 2 root x minus 2 root a is equal to 2 root x. I am going to take everything to the other side and leave a 6 alone. So I have a 6 is equal to, this was positive that side, so it's going to be negative there, 2 root x. And then this one was negative, that side is going to be positive, 2 root a. And then this one is still on the same side, so it's plus 2 root x. This plus and negative, these two will cancel out, and you are left with 6 is equal to 2 root a. Of course, I can divide by 2 on both sides, and this 2 and that 2 will cancel out. And now you are having a 3 is equal to root a. And once you are having that, you can rest assured that I want to remove this root, so I just have to square on both sides, and then I have a root of a, and then I have to square that side, and then I have a 9 is equal to a. So that is the value of a. And because I'm having that, I can guarantee you that I am going to end here when it comes to the fundamental theorem of calculus. I hope you understood what we were actually doing here, because this is actually the missing piece, and it also plays a crucial role when it comes to making the when it comes to use substitution. If you understood how we ended up solving D and C in this particular question. A quick recap: we wanted to find the function f and the number a such that this happens, but now to solve for this, we found out that we have integration. So when we are having this integral and want to solve for that, we need to remove the integral by taking the derivative throughout. But what is the independent variable? The independent variable, we saw it from that side, and we also saw it from one of the limits of the integration. So we derive with respect to x, so we derive on both sides. The derivative was 0, and when we're taking the derivative of that part, we saw that we can use the theorem, the fundamental theorem of calculus. We have dx, we have x, which means just replace the t by x, and then you end up getting that, and there's also t there, replace it by x, and then we take the derivative on the right the normal way to get that, and then we simplify, then we cross multiply. After cross multiplying, you just simplify, and then we got that. The next thing, we go back to the given equation, which is that, but now we replace this f of t by what we found, and then we take the integration the normal way, and then so that we can actually get the a as part of the equation and solve for it. That's what we did here. It's not a big deal, it's very straightforward. I hope you can understand what is going on here. Thank you when it comes to this. Now we will talk more about in our next lesson, we will talk more about indefinite integrals. And definite integrals, in simple terms, it is the most general antiderivative of a given function. That is the simplest as at its best. That's what we will do in lecture 53, and I hope you'll still be interested in that. Let's stop there.